This lesson is going to review ionic and covalent bonding that you would have learned in grade 10. Let's review a few ideas about chemical bonding. First, you need to know that chemical bonding occurs through the forces of attraction by means of valence electrons. This is why we've been talking about them and aware of how many valence electrons our elements have. It's very important that you are able to know that. There are two kinds of bonding. We know this. There is ionic and there is also covalent bonding. There's also a third called metallic. We get into that in the grade 12 course if you decide to take it. And one of the trends in the periodic table that we talked about was electronegativity, and we have to recall that. That is going to be important, particularly in covalent bonding. So just a reminder that that term refers to the attractions for electrons in a bond, and they are numerical values that you'll find on the periodic table. The higher the value, the more attractive that element is for electrons. So it will grab electrons closer to itself. The lower the value, it means that there's not a lot of attraction for electrons and they get taken away from that element. Okay, let's fill in all these blanks for ionic bonding. Many of these you know, and this should just be review. Ionic compounds are formed when one or more valence electrons are transferred from a metal to a non-metal atom. So you need to have one of each. You need to have a metal and a non-metal in order to carry out ionic bonding. The metal atom is going to lose his electrons. Metals have low electronegativity. They have low attraction for electrons. And when he loses his electrons, that means he's going to have more protons. So he becomes a positive ion, which is called a cation. The nonmetal gains its electrons, again, has a higher electronegativity, so that means it has more of an attraction for electrons, and it becomes a negatively charged ion, which we call an anion. So these two ions, the cation and the anion, are attracted to each other by electrostatic forces. Remember, electrostatic is the attraction of positives and negatives to each other. And elements try to obey the octet rule. Okay, and what this means is they are trying to gain or lose electrons so that they have a full outer energy level that tends to be 8 electrons. One of the things that we also can refer to here, and I'm going to put a little delta sign there, that the difference in electronegativity between these two elements should range between 1.7 and 3.5. So we'll just comment on that. That is rarely needed actually to do that math for ionics because you can tell right away whether you have a metal or a non-metal. This range here would be important if you had a metalloid. And with a metalloid, you're trying to determine whether it's behaving like a metal or a non-metal. This difference in electronegativity will help you determine that. When we show ionic bonding, there's two ways to do it, and you can use Bohr-Rutherford diagrams, although it's not often used simply because it's too much work. You have to draw all the energy levels of each of your atoms, and really all we care about are these valence electrons. So why would we show all of these inner energy levels, all these inner electrons? But the idea is the same, that sodium is a metal. He's going to lose his electron and it's going to go over to chlorine. And the idea is that any single electrons are paired. You have to pair up single electrons. So the rest of those electrons that you see in chlorine right here and here and here, they're all paired up, so we don't worry about it. When sodium loses his valence electron, you notice that he reduces in size. Remember we talked about ion charge or ion radius because he's lost that whole outer energy level. He has a positive charge because he's lost an electron and he now has one extra proton. And chlorine has a full outer energy level as well. and a negative charge because he's gained an electron. Typically, we'll use Lewis structures. It's much faster and it's easier to show the bonding. So you go to the periodic table, you see that sodium is sitting in group 1. We know he'll have 1 valence electron. You look up chlorine on the periodic table. He's sitting in group 17. He does not have 17 valence electrons, but he has 7. So we put those 7 valence electrons around as singles, come back, pair them up to get to 7. We show that sodium loses his electron over to chlorine, and we indicate that by putting an X to pair up that single electron of chlorines. We don't leave it like this, we clean it up, and we show the ions. It's ionic bonding, right? We need to show that there's ions being formed. So sodium now has no valence electrons in his outer energy level, so we don't draw any. He has a charge of +1. Chlorine has all of his electrons in the outer energy level. We show them. And he has a charge of -1. Let's do one more example between magnesium and chlorine. So we look at magnesium on the periodic table. He has 2 valence electrons because he sits in group 2. So we draw them in as singles. We show chlorine, we show chlorine with, again, 7 valence electrons. So we show those 7s as singles. And then we have pair them up, and then we have 1 single electron left over. We're going to take one of magnesium's single electrons and we're going to pair it up with chlorine's single electron. And chlorine's good. All of his electrons are paired. This is the goal. That atom is happy. We don't need to do anything else to it. But magnesium still has this 1 electron left over, and we have to pair that up. And if you're doing bonding, you're going to have tons and tons and tons of atoms present in order for magnesium to find another chlorine and then give his electron away to a second chlorine atom. So you need to show this, that you get a second chlorine, and then we do our ions. So magnesium has now lost 2 electrons. He has a charge of +2, and chlorine has gained 1 electron with each atom. So we show a charge of -1, and we have to do this twice to show that both of those atoms gained an electron and have a charge of -1. When you look at this, these charges balance out, okay, +2 and then -2 over here. And you can come up with a chemical formula as well. You have 1 magnesium and you have 2 chlorine atoms after you do that bonding. Let's review covalent bonding. Covalent compounds are formed when 2 or more non-metal atoms, so only nonmetals, share electrons. So this is different than ionics. Ionics is a metal and a nonmetal. They transfer electrons. Covalents are 2 nonmetals who share. When they share their electrons, they can result, this can result in compounds that may have single, double, or triple bonds. Not sure how much of that you saw in your previous course, but we'll see maybe single or double bond. Well, it's definitely single, maybe double bonds in this course. Elements are still trying to obey the octet rule. So they are still trying to pair up single electrons in order to get a full energy level. And we know when we have a full energy level, we have 8 electrons. Here, their difference in electronegativity ranges from 0 to 1.7. So let's show some bonding that occurs between 3 different sets of elements. We're going to have to do a couple of extra examples here just because covalent bonding, there's a lot more going on in it, and you can have different combinations of elements and different types of bonds. So we start as usual. We want carbon and chlorine. So we look up carbon on the periodic table. He is sitting in group 14. He has 4 valence electrons, and we always place those as singles first. We then grab a chlorine atom who has 7 valence electrons. And now we match up the singles. We do not transfer electrons like in an ionic bond. These are 2 nonmetals. And so we share electrons, and we show that by drawing a circle around them. So chlorine's good. He just paired up his single electron. He's got 8. Carbon still has those 3 single electrons, and so we know what to do. We know that there will be lots of other chlorine atoms around, right? A sample of these elements will provide millions of atoms in order for you to find another chlorine and to keep going and to pair up any of these single electrons so that everybody is paired up and everybody follows the octet rule. So by sharing those electrons, everyone now has 8. And this is very messy looking. We clean this up. Anywhere where you have put a circled pair of electrons, you are now going to replace that with a line. So you paired up that electron at the top of chlorine or of carbon, and so we replace that with a line. You paired up a single electron to the right of carbon, you replace that with a line. And then at the bottom, and then to the side. Okay, and that is what your covalent molecule looks like. Let's do oxygen. So oxygen is sitting in group 16. He has 6 valence electrons. So we place them again, singles first, and then we go around and pair them up. So oxygen has 2 single electrons, and if he's not bonded with anything else, he's going to bond to himself. So let's draw another oxygen, and let's pair up any of these single electrons by sharing them. So there's a share there, and I'm going to stretch this and share on the other side as well. So again, this looks messy. We don't want to leave it like that. Anywhere where we've shared electrons, we replace that bubble with a line. So I'm going to redraw this and clean it up. I'm going to put 1 oxygen there, and I'm going to show the fact that they shared electrons like this side by side. And I'm just doing this as a baby step, and we're going to replace that now with 2 lines in between oxygen. And then don't forget about those other pairs of electrons that exist around oxygen. And notice how I've drawn them. Electrons want to repel. Okay, so they will pair up with each other. The reason that they do that is that they spin in opposite directions. So they kind of create a little magnetic field around themselves, which will allow them to pair up. But then when they're paired, they are a negative cloud of energy that wants to repel all the other electrons. So you want to be mindful of that when you're drawing these. Let's do phosphorus and fluorine. Okay, so phosphorus sits in group 15. He has 5 valence electrons. Fluorine is a halogen sitting in group 17, 7 valence electrons. And then we're going to pair up any of my single electrons. And again, over here, pair them up. And notice that right here, that phosphorus has 2 pairs of electrons on its own. Don't separate those. Once they're paired, they're very happy. They don't want to split up. And we're going to redraw this molecule. Do not forget those electrons at the top of phosphorus. And then we're going to bond our fluorines to all other locations. There you go, a review of ionic and covalent bonding.